Listen-only mode.
To the inaugural Arctic Research Seminar Series from the Arctic Research Consortium of the United States, ARCIS. And welcome to the new DC office of ARCIS. My name is Bob Rich, and I'm the Executive Director. ARCIS has been working for more than 25 years to connect Arctic research across boundaries through communication, coordination, and collaboration. We're a nonprofit consortium of organizations and individuals interested in advancing inquiry, discovery, and understanding of this really important region and informing sound decision-making through that research. This seminar series was conceived to provide unique access to some of the leading Arctic researchers for federal officials, members of the DC policy community, and the broader public who are interested in the rapidly changing Arctic. The ideas shared here represent the cutting edge of what we're exploring and learning up north, and also what it means for the U.S. and the rest of the world. I encourage you to take a look at the ARCIS materials that you were handed when you arrived, if you were here in the room, or to take a look at our website at www.arcis.org. And afterwards, we'd be happy to discuss any questions you have, or love to hear how we can best help you to succeed. We're currently joined by looks like more than 75 people. They keep coming in online throughout the United States, in Russia, Greenland, Denmark, Canada, the UK, and Switzerland, in addition to hopefully about a dozen so here in DC. For those of you on the webinar, my colleagues are available to answer any questions you have about ARCIS or Arctic research, and to forward to us here in DC any questions you have for Julie. Just type your questions into the box on the right, and we'll start addressing the questions after Julie has finished her talk. Whether you're here or online, we invite each of you to become an ARCIS member. Currently, academic institutions, government agencies, corporations, and indigenous organizations are eligible to become ARCIS members. Also, any individual who cares about the importance of Arctic research, such as yourselves, can become an individual ARCIS member. And so I'd invite you to join us, and you can see information on membership at www.arcis.org. So with no further ado, let me introduce our speaker. Dr. Julie Brigham-Grette is a professor of quaternary and glacial geology at the University of Massachusetts Amherst. She's been there since 1987 and is currently the department head for geosciences. Her CV is very impressive, but I know you don't want to hear me. So I will just try to, Julie is a fellow of the Geological Society of America and has served on the National Academy of Sciences, National Research Council's Polar Research Board since 2008. She's currently the chair of that prestigious body. Her presentation today is entitled Sea Level and Polar Warming, How Past Climate Change Informs Us About Ongoing Sea Level Rise. Please join me in welcoming to DC and the Arctic Research Seminar Series, Professor Julie Brigham-Grette.
All right. Thank you. All right, thank you very much, and welcome to those here in the room, but also to those who are on the webinar, and look forward to hearing your questions afterward. So I'm going to talk about some of the information that is certainly emerging here recently about the vulnerability of our ice sheets. But I'm going to talk about it from the perspective of not as a glaciologist, but as a glacial geologist, talking about what we see as evidence for the vulnerability of these ice sheets from paleo environments. And I want to start with this little animation here. Give me a minute to get it started. I'm a little clumsy at it. There we go. Okay, so first of all, we want to talk about the human impact of carbon dioxide and greenhouse gases on our planet. We know, everyone knows that these are causing the Earth to warm, and I just wanted to give you a bit of perspective about where we're at here. On the left, you see a dancing line going up and down. On the far left is the monitoring station at South Pole, and on the right, or in the middle, you see a red dot, and that is the monitoring station for CO2 in Mauna Loa. And all the other little dots are other recording stations for carbon dioxide throughout the world. And you see that the northern hemisphere, the right-hand side that's wagging the most, is actually driving the carbon dioxide of the world up more and more. And that's the seasonal cycle of the Earth photosynthesis and decomposition that goes on and the large land areas and to the north. On the right-hand side of the screen is the accumulation of that CO2 record, with the red wiggle up and down being the Mauna Loa site. And now we're going back through time using the ice core data to look at carbon dioxide that's preserved as essentially fossil air in the ice cores. And we can see now we're going back 500 or 1,000 years, and we're now going to go back in time to the last ice age. There's 20,000 years ago, 40, 50, 60,000 years ago. And you can see that CO2 through the glacial interglacial cycles normally oscillates between about 180, 280, 180, 280 parts per mil. Even if we go back through the last 800,000 years, as we do here, you can see how outside of the box we are right now. We're at 400 parts per mil. So we really are, humans have really pushed us outside of the normal envelope that the world would experience on glacial interglacial timescales. And so what are the repercussions? What's going to happen to our ice sheets as we continue to warm the world in this way? It's not a new story. We knew about the greenhouse effect more than 150 years ago. And here's an article from 1956, when I was only 1 year old, talking about a warmer climate on Earth, maybe due to carbon dioxide, and how even back then we knew that there were consequences about this. And so if we look at a diagram like this, many of you have probably seen similar figures. This figure shows you the effect of polar amplification, the fact that as the world itself warms up, it's the Arctic regions that are amplified in that warming. They're warming faster than other areas. So even though the global warming may be only 1 or 2 degrees on average, the increase in temperatures in the high latitudes is actually much more than that. If we take a line north-south from the southern hemisphere down from Antarctica all the way to the Arctic, here now plotted on an XY plot shows you the zonal differences in that. And on the right-hand side of the diagram, you can see how the amplified effect of the temperature is increasing in the Arctic as opposed to other regions. So we're quite concerned then about how that amplified warming is impacting our sea ice and also the other aspects. And we see this recorded in a lot of different proxies. For example, the Arctic is greening. There are parts of the Arctic now that are flourishing with shrubs, and tree line is moving northward to the effect that it's like moving Winnipeg down to Minneapolis. That's kind of the range of scale we're seeing the migrations of plants as the world, as the north warms up. And of course, we all know that the Arctic sea ice is decreasing, and this animation, which actually was just updated on Wednesday, I didn't happen to get the newest one that includes 2015 into it, but we see that the whiter colors here on this animation are the thicker multi-year sea ice, which is usually in the range of 2 to 3 meters, can be buckled up to in places like 6 or 8 meters. And then the lighter blue or the darker blue colors are the single first-year ice. And what we see through time, this is now 87, 88, shows you how that circulation has changed over time, but particularly as we come into the recent decade, we see that the multi-year ice has decreased dramatically, meaning that we have an Arctic that's full of largely first-year ice, which is much more susceptible to disappearing. And you can see how that has taken over dramatically. And this video has a lot of meaning for me because I first did a lot of my field work in the Arctic in 1980, and I spent a lot of time being stuck in sea ice near Barrow, Alaska, and that would not happen today. So let's think about that warming, what that warming has for implications on ice sheets. And we can just think about, well, and as ice sheets melt, of course, sea level will rise because the meltwaters are going into the sea. And so how do we raise sea level? There's 2 ways: thermal expansion, so we have about 0.4 meters per degree centigrade as the Earth warms up. That's one way to expand the raised sea level. But the larger one, of course, is the ice sheets and the glaciers. And there are locally other things like subsidence or the extraction of groundwaters. For example, in New Orleans, the ground in some areas of the Ninth Ward is dropping as much as 15 centimeters, 10 to 15 centimeters a decade because of the extraction of groundwaters and also because of the sediments coming down the Mississippi River that are loading that area in New Orleans. So you might think that the levees themselves aren't high enough. It's because they're also sinking with the regional landscape. So we were concerned with what's happening with Greenland. With Greenland, for example, here in 2012, there were actually 4 days in the middle of July when the entire ice sheet on the right in the center of the figure here was completely in the melt zone. We want to see how often that's going to happen. And of course, we're taking, we have scientists from NASA and many other parts of the academic community watching what's happening to Greenland and the acceleration of some of the glaciers there in that region. And this, see if I can get this to work. This is also a little animation that you see the darkening colors happening here to show you the melt rates in Greenland and the areas of Greenland that are melting most dramatically here in the red colors. At the top of the screen, for those of you looking at this online, later on, you could, if you make a copy of that link, later on, you can, this is a new video that came out just recently about showing the melt rates. That's actually a better one than this one is now. The same kind of data about melt rates is also online from the GRACE data from NASA, I guess. And this shows you also that the largest melt rates that are happening in the southern hemisphere in Antarctica are happening on the West Antarctic ice sheet, that there's tremendous vulnerability here in this part of the ice sheet and up through the Antarctic Peninsula, where we've seen many of our ice shelves decline. 7 out of 12 ice shelves have been lost or are in decline just in the last decade or so. And we think this is largely because of the tremendous meltwater, warm water that's actually coming up back underneath the ice shelves and melting them from the bottom, as well as we're starting to see more melting from the top of these ice shelves. And these ice shelves are important because they buttress the ice behind them in the ice sheets behind them and hold these ice sheets back from a more rapid decline into the sea. So this actually shows us a little bit more dramatically. The picture on the right is of Antarctica, and all of the red zones that you see here are the large floating ice shelves that are buttressing, holding back the flow of the ice. And on the left-hand side, you just see this kind of Gothic architecture, the idea that these buildings would have collapsed had they not had these flying buttresses, so-called flying buttresses on them. We remove those buttresses, these buildings would collapse. And that physics was known centuries ago. But in our ice sheets today, these ice shelves operate the same way. They are buttressing the flow of these ice sheets. And as we saw in a couple of papers that came out almost 2 years ago, 18 months ago, that parts of Antarctica are now in what we think might be unstoppable retreat. So the ice shelves are gone, and the ice flow is accelerating. Now, let's think about the context for that. In the last the IPCC report that came out just a while ago, there were a number of different scenarios for carbon dioxide and the implication for that. These are called representative concentration pathways. And you'll see on the left hand, on the XY plot here on the left is year 2000, and on the right is 2100. And then the scale on the y-axis here is from 350 parts per mil up to over 1,000 parts per mil. And the worst case scenario, which is actually called the business as usual, is the RCP 8.5. So that shows that we don't change what we're doing. And then there's some other moderate implications here for these scales. But I want you to see the minimalist, where we reach a maximum of CO2 in the atmosphere here in the next decade or so. That's the 2.6 scenario versus the 8.5. And here on this graph is the projected estimates in the IPCC for what sea level is going to do. And you see that in both scenarios, sea level is still rising, and in the case of the 2.6, we see a modest sea level rise of only 60 centimeters, but in the more business as usual, maybe approaching a meter is predicted by 2100. And I want you to remember those numbers because as we get to the end here, I'm going to show you some new evidence that's coming out to suggest this may in fact be extremely underestimated in terms of sea level rise. So where are we if we're at 400 parts per mil today with our atmosphere, where does that put us? And this might be a little bit difficult for some of you to see. If you just look at this top diagram, this is on the left-hand side, almost 4 million years ago up to the present here. These are estimates of carbon dioxide. At the top of the diagram in red is the Lasecki-Ramo oxygen isotope stack, which many scientists use as a proxy for climate change. And if you don't understand any of that, the details there, it's simply when that wiggle goes up, it's warmer. When that wiggle goes down, it's colder. So warm, cold through those wiggles. And then we've tried to estimate paleo carbon dioxide through these different time periods through here. And we can see that today, we've actually gone back to the Pliocene. We've gone back to the last time when we were at 400 parts per mil in the atmosphere. We were back at around almost 3 million to 4 million years ago. So we're in the Pliocene in terms of our atmosphere today. So should we be worried about that? What do we know about what ice sheets do at 400 parts per mil? So I thought, since this was the inaugural talk for the ARCUS group, I wanted to take us back to my beginnings in the Arctic. I started working on the North Slope of Alaska, mapping paleo shorelines, the sea level history of the north of the Bering Land Bridge. And my mentor at that time was David Hopkins, Mr. Beringia. He really was the first person to suggest there was a land bridge in a paper in Science in 1955, the year I was born. And working in a number of different areas, he was mapping these shorelines, looking at the fossils, looking what the fossils told him about the oceanographic change through the Bering Straits. And we worked together in a number of areas before he passed away. But tremendous knowledge of looking at what these shorelines were like and through time. So a number of us who were mentored by Dave have updated a lot of the sea level change. And I just want to point out here, on the top part of the diagram, you'll see a series of benches with these numbers on them. These are shorelines that are mapped around different parts of the world. And on where the land is tectonically uplifting, like the coast of California, you see these high sea level events through time because they've been uplifted by tectonics. In Alaska, we have some tectonics, but not as much. And we tend to see what we see, the stair steps on the lower diagram, where we see certain high sea level events over time. And that's what I'm going to show you today, that we know something about that. And we've mapped these not quite like bathtub rings around parts of northwest Alaska and northeast Russia. Now, Daryl Kaufman, working in Nome, and myself on the North Slope, with also people from the U.S. Geological Survey under Dave's mentorship, we mapped these different shorelines. And I just want to show you that these are 5 or 6 of the main ones and the ages of them. But I particularly want you to see that over time we've seen sea level at 7 meters, 8 meters, 22 meters, 30 meters above present, 40 meters above present in the past. And so when I was mapping these shorelines 35 years ago, I thought something must have melted. How could I couldn't explain their elevation without having to melt parts of Greenland and Antarctica. So 35 years ago, I wondered what melted to do this. And so here's just a cartoon in the lower part of the diagram taken through a transect from right near Point Lay, west of Wainwright on the North Slope of Alaska. This is a transect of the landscape there. And you can see these different benches outlined here. And in those deposits on the North Slope, we find mollusks, bivalves, both gastropods and mollusks, that live today in south of the Aleutians or in the Sea of Japan. So it told us that when up in the Pliocene, when CO2 was 400 parts per mil, when there probably wasn't any Greenland ice sheet, and when the sea surface temperatures off Barrow, Alaska, were 9 degrees warmer than today. So much warmer water in the past when in a warming scenario. And we could see, just like today, with ecosystems, marine ecosystems moving northward, fisheries moving northward, we see this in the paleo record. We see these ecosystems, marine ecosystems, have moved in the past to the north, and we can trace them because their fossils are left in deposits in Barrow and all the way around to even Prudhoe Bay. So I got into a debate in those years, 30 years ago, about what could have melted. And I went to a conference where we were discussing what was happening with Antarctica. And at that time, there was a raging debate between George Denton, Dave Marchand, and some others about the stability of the Greenland ice sheet. And there was some deposits there. I won't tell you the whole story, but there was some deposits there that if they were in fact 3 million years old, then these deposits would suggest that part of Antarctica must have melted for these deposits to exist. George Denton and others were saying, no, these are 15 million years old. The Antarctic ice sheet's been stable forever. And in fact, I can distinctly remember, and I say this with fondness for George Denton, he said to me, Julie, you don't know anything about your shorelines. Just sit down because the Antarctic ice sheet has been stable for 15 million years. So this was 30 years ago. So now we know that things are a bit different. That we know that, in fact, the gravity field of the Earth changes the relationship of sea level around the planet, that, in fact, we know that, in fact, ice sheets themselves have gravitational pull, and so that as ice sheets melt, there's great complexity in how sea level changes over time. And, in fact, this map shows where shorelines might be predicted for one of these warm periods about 410,000 years ago. And, in fact, this shows, again, with the changes in the gravity field, how, in fact, at least part of the elevation of my shorelines is because of these changes in gravitational pull. But at the same time, it still seems to be of concern that sea level may have been 8 to 10 meters above present 410,000 years ago. So the question comes back, what melted and how did it melt? So let's take ourselves now back to the Pliocene, back to that 400 parts per mil world. What did the Pliocene look like? So this has been an area that I've worked on throughout my parts of my career. And what I particularly want to point out here is the fact that there's a number of deposits around the Arctic, these little yellow dots around here, show you places where around 3 million years ago, plus or minus 500,000 years, there are deposits that show that the Arctic was much warmer in the past, in the Pliocene. Temperatures here in northern Ellesmere Island were like Anchorage today. So growing temperatures 14 degrees warmer. And there's amazing deposits with fossil camel and beaver showing that, in fact, the ecosystems were very different. And we have pretty good evidence that the forests went right up to the Arctic Ocean 3 million years ago or so. So at that time, there was no, as you see, there is no Greenland ice sheet. There may have been glaciers on the eastern coast of Greenland where there are high mountains that were providing extracted debris into the sea. But it was a very different kind of Arctic back then. So we had deposits around the Arctic that told us about what was happening and how warm it was, but we didn't have a complete record on land of what this was. And so we discovered a place in northeast Russia, and this was brought out by Olga Vyshkova, who was part of the Russian Academy of Sciences in Magadan, who told me about this basin in northeast Russia located in the center of Chukotka, where this meteorite impact hit 3.6 million years ago and created a crater that then has since been collecting sediments and organic matter and fossils of various kinds all through the last 3.6 million years to give us an idea of what the climate was like in the past. So in our first indication that this was a fantastic record is based on these wiggles here on the left. This is the insolation curves. The one here is the Dome Sea record from Antarctica of temperature, and then this one here is Lake Baikal, and then the last one on the far right is our biogenic silica from our Lake Elgagikin record, from this record. And what was remarkable to us when we first got our pilot cores was, in fact, there was similarity between Antarctica, Lake Baikal, and this lake that nobody could pronounce in the middle of nowhere in Russia. So we knew that we had something that was collecting and giving us information on a global scale. So just a moment to mention, of course, a project of this dimension is not something I do by myself. We had collaborators from Russia, from Germany, and also from Austria. And this was a major effort put forward for the International Polar Year. And so no one country could have done this alone, and we're certainly very proud of that effort. This cartoon shows you where we did the drilling in the center, roughly off, just slightly off center from the center of the lake. And you see there's 3 cores, A, B, and C, which together make a composite record back 3.6 million years ago. So this is the kind of sediment, and I might mention this, the crater itself is about 18 kilometers across. The lake today is 12 kilometers across, and the lake is also about 175 meters deep. That's if you took the George Washington Monument out here just a few blocks away and stuck it in the lake, the very tippy top of George Washington Monument would stick out of the top of that. So that's how deep that lake is. So let's look at the long term here, and then I'm going to highlight just a few of the time periods that we want to look at and then talk about ice sheets. So in this figure, this is the main wiggles here, warm and cold, warm and cold, warm and cold over time. This particular figure goes back about 4 million years ago. It's produced by the Pliocene curve that is a composite of all the world oceans. So this is our kind of our Rosetta Stone for information about climate change. And again, you can see on the right-hand side where the thermostat sits, we have higher CO2. And you see the climate change is kind of muted, warm and cold, warm and cold. And then as we move to the left in this figure, we come back to 2 million years ago, 1 million years ago. We're getting into the full ice ages, glacial, interglacial change, warm and cold. The red stars at the top of that diagram that hit the tops of the warm periods are what I'm calling, our group is calling superinterglacials. These were extremely warm times at the Lake Elgin site when we saw forests come all the way back around the lake. Today the lake is surrounded totally by tundra, as you see in the lower left part of the diagram. That's what the lake looks like today. The picture in the middle is kind of this is actually what it looks like in winter, but it gives you an idea of what it may have looked like in glacial summers 20,000 years ago, for example. And then on the far right is maybe what it looked like during these superinterglacials. So we wondered from this record, our main questions there were, I don't think I'll go back, were, what is it about the Arctic? Did the Arctic have the same kind of record that the Pliocene curve was showing? What was different about the Arctic, and could we see evidence of polar amplification through time? So the bottom line is yes, we see a lot of polar amplification. In this figure, this shows you the change in vegetation through time on the right-hand side of the figure. Over here on the far right-hand side is about 3.6 million years, and on the left-hand side of the diagram, we're at about 2.2 million years. So these color bars are just a simple way of showing you how the forest changed through time. That we didn't come along and have forested conditions and then suddenly abruptly change into a landscape of tundra. Rather, we went through cold mixed forests and then deciduous coniferous forests and then back into those warmer forests, and then gradually through time, by the time we came to particularly about after 2.4 million years ago, we started to have more continuous tundra like we're expecting. So during this time, so what this shows you is that during this time when the carbon dioxide in the atmosphere was up around 400 parts per mil, we had much more forested conditions. And I particularly want to point out, this is hemlock, fir, tree pine, larch, and even walnut trees in northeast Russia at this time. So this is a very different kind of environment than it is today. So, climate scientists like myself like to show changes in climate with wiggles, again, warm and cold, up is warm, down is cold. And I just want to show in this figure, here's in the green line, and let me start here. At the top is the Pliocene, that global stack of warm and cold times. In the green, what you see is our best estimate based on the pollen data from the lake. It shows you the summer mean temperature. So this is like July in the Arctic at this site. And the blue line shows you precipitation. And we think this index is it's the site's annual precipitation. And so you'll see that at about 2.73 million years ago, there was a radical change in the amount of precipitation coming in. So we saw a bifurcation between warm and wet, cold and dry. We went into still warm but drier, so less precipitation. And our hunch is what could possibly cause this may have had something to do with sea ice. These red lines coming across each of the red lines and the blue lines here, the precipitation and the summer temperature, gives you an indication of what the site is seeing today. So you see that all through this time period, 3 to 2.2 million years ago, summer temperatures were much warmer than today, and also for most of the time before 2.7 million years ago is much wetter, much more higher precipitation. So we have some work by some of our graduate students also suggesting in the upper part of this diagram, this is the precipitation diagram you just saw for that time period. And these are leaf wax deuterium data that suggest, again, changes in the source of moisture, again, related, we think, to sea ice. And on the right-hand side, Sebastian Koenig here, who's pictured, has done some modeling experiments that he's published that show, in fact, that if you get rid of the sea ice in the Arctic, and if you warm the sea surface temperatures up, his modeling suggests that you can get rid of most of the Greenland ice sheet within about 5,000 years. So, but again, remember, even losing a meter of sea level from Greenland, which could happen quite rapidly, sea levels would rise quite dramatically. But in fact, so getting rid of that sea ice and warming those sea surface temperatures has a dramatic effect that we can reproduce in models. And we can see if we, here just to show from modeling experiments, these are two panels that show reconstructions of the vegetation in warm and cold orbits. And again, the main point of this figure is that the bottom two panels on the left and the right, where the circles are, it shows that in the modeling space, we can keep the forested environment at the lake at 400 parts per mil. But if CO2 is less, we can't keep the forest there. So again, our paleo data is showing us that in fact it makes the most sense. CO2 was 400 parts per mil in the past, and that's why we had forested conditions, and probably no Greenland ice sheet. These are some recent reconstructions, not by myself, but by others, of roughly through this time period, again, from the Pliocene, again, reproducing that this time period did in fact have carbon dioxide around 400 parts per mil. And in fact, you can see some of those estimates are even a lot lower than that. So we've almost exceeded some of these past reconstructions. So now I'm going to really quickly here just go through a couple of other things that we're seeing. And a particularly important bottom line of what I want to say today is that we see an amazing coincidence that the superinterglacials in our Arctic site in northeast Russia seem to be matching the times when we lost the West Antarctic ice sheet. So we could prove it for a couple of time periods, and we're testing out whether that works uniformly through other time periods. On the left, you see a reference to the Andril project, the Antarctic drilling project that took a couple of deep boreholes, particularly beneath the Ross Ice Shelf, and on the right, the logo for the Lake Elgin-Dickon project. Both of these were large international efforts supported by the National Science Foundation, along with science agencies in other countries. So in the Andril project, they could reconstruct in this panel in the center, you see that when the ice sheet pulls back, and there is no West Antarctic ice sheet, and so you see the drill rig suspended over the water there in the cartoon, when the West Antarctic ice sheet disappears, you get nothing but diatomaceous ooze, or diatoms that are living in the surface waters, preserved beneath the Ross Ice Shelf. But when the ice advances, you start to get glacial till. So my point with this slide is that whenever in the next few slides you see yellow diatomaceous ooze in their record, that means there is no West Antarctic ice sheet at that time, or at least it's retracted a great deal to allow diatomaceous oozes to be deposited. So here in this figure on the green line is the one you've seen before, the Pliocene world going into the early Pleistocene, showing you mean annual temperatures at Lake Elgin-Dickon. And in the bottom panel here, you see green bars and yellow bars and even some orange bars that represent the sediments and underneath the Ross Ice Shelf. And what I want you to see particularly is that there is a number of time periods. Here's this little cold snap in our record. It didn't quite get as cold as you might think, but this is a time when this M2 event, this major re-advance of the Antarctic ice sheet, occurred at around 2.3 million years ago, after a period of over 1 million years when there was no Western Antarctic ice sheet. And then as we move to the left in this diagram, here we see there are a number of individual, these yellow deposits in this figure. These are the diatomaceous ooze when there was no Western Antarctic ice sheet. And they may, in fact, match with almost these superinterglacials through this interval of the core. You'll notice that on purpose, the red lines where I'm trying to make the tie points don't go all the way because there are unconformities in the interval record that prevent me from making an honest match because of the dating variability in there. But I like to say when I'm by myself, I can match those up. But honestly, I would not be able to defend that to the science community explicitly. But it looks like, smells like they match, right? Okay, it looks like they do. Now, I want to zoom into the more recent time period very quickly here and look at the top bar are sediments at the lake. And I just want to say these red boxes represent the time periods from the present on the left side and back to 2.8 million on the right-hand side that show us when we had superinterglacials in the past. And then here's the Lisecki-Ramo curve, this one here with the warm and cold periods. And again, here's the Antarctic record here. And I want to zoom in particularly on these four time periods here. Marine isotope stage 31, which is about 1.1 million years ago, and then another one on stage 11, and then the more recent warm periods. And again, stage 31 is our best match between the warm Arctic and the demise of the Western Antarctic ice sheet. This is where we have the best age control because of some magnetic reversals in that time period. So here on the top, I'm showing reconstructions for Greenland for these time periods. First of all, on the left, the Holocene, the recent time period, and then 5.5, that represents the last interglacial, 125,000 years ago. Stage 11 is 410,000 years ago, and stage 31, 1.1 million years ago. In our reconstruction for the last interglacial, the 5.5 you see here, most scientists would agree that we got at least 1 to 2 meters of sea level out of Greenland back in that time period. Now, you see from this record, from our temperature and precipitation data, that in the past, in stage 11 and stage 31, the Arctic was much wetter and much warmer than we ever imagined. And this would suggest that, in fact, maybe Greenland really shrank considerably during these previous interglacials. So this is a challenge to those in Greenland looking at, is there evidence that, in fact, those ice sheets were much, much smaller? But particularly want to focus in on stage 31 very quickly. This is a paper that just came out this week in Earth and Planetary Science Letters by Greg DeWitt, one of our PhD students at UMass. And what he's been able to show is that oxygen isotope stage 31, which I just explained was quite warm, was a long interval, maybe 50,000 years long, when we had this superinterglacial. And at the bottom of this figure, the green line here, these wiggles here, are showing through this interval. The pink band is a time when there's absolutely no ice-rafted debris around Antarctica. So that means the Antarctic ice sheet had retracted so much that we didn't have a lot of ice-rafted debris. At the same time, we have this long superinterglacial in the Arctic. So this is our absolute best match, that what's happening at the two polar regions is actually synchronizing. And in fact, and so that these ice sheets can actually come and go. That's my bottom line of my message today is these ice sheets have come and gone before. So the fact that they're collapsing now should not be a surprise. And Greg has correlated this around the world, and I invite you to take a look at his paper in the Earth Planetary Science Letters. I won't go into that. But this is a reconstruction that Rob DeCanto, my colleague, has put together for what Antarctica looked like in isotope stage 31. This is, again, the modern ice sheet in the model versus on the right is the reconstruction during 1.1 million years ago, when the West Antarctic ice sheet, for the most part, probably had retreated very quickly, again, causing sea level to rise. And this explains at least part of the shorelines that I was matching in Alaska over 30 years ago. So some of our questions were, is the Arctic terrestrials record similar to the global record? Yes, we have a lot more to learn about that. Are there links to the Antarctic climate? I would argue that yes, and I have only explained a couple of the coincidences that we see between the Andrill and the Lake Elgevikan record. This diagram on the lower left is from Andrea Dutton's recent paper about reconstructing sea level, and she has here a small little green dot showing you carbon dioxide and the range of sea level here 3 million years ago. On the right-hand side of her diagram, showing that sea levels perhaps in the range of 20 to 30 meters above present in the Pliocene. That's still a debate the science community is trying to work out because, again, sea level, it's very hard to map exactly where the position of that shoreline on different parts of the landscape because of those gravitational issues I mentioned earlier. So that's an ongoing area to research. But clearly, if we go back to a 400 parts per mil world, we're approaching a world, in fact, when sea level must get much higher. Now, if you think about, we have a lot of coastal cities around the world that are within a few meters of sea level, not to mention the Washington, D.C. airport, among others, that we're very close to sea level. But there are also major large cities around the world that are also within 5 to 10 meters of sea level that we need to worry about that infrastructure. And certainly Hurricane Sandy showed us what could happen even with a serious storm surge. And if you add these storm surges onto the rising sea levels, we're in for a lot of either retreat or some kind of other coastal management that's going to be required. Richard Alley and others hinted about this even in the paper in Science in 2005, where they showed here's where we are now, 400 parts per mil. The diagram shows you carbon dioxide along the x-axis on the top, and on the right-hand side is sea level. And if we go back to the last glaciation, when the Earth was cool, we were down at the sea level was down at around 120 meters or so, 120, 30 meters or so. We come up to the more recent present, pre-industrial levels at 280 parts per mil. Sea level being there at 0, and then now we're at 400 parts per mil, and you can see that sea level, that line, enters close to a dot. It is a best estimate for what Pliocene sea level is like. And so the problem is, this is where our coastal cities are. And if you were at the Arctic Matters meeting yesterday, Richard Alley made this point, that in fact a lot of our coastal cities are in this zone where sea level is heading. So we've got to be concerned, and we have to appreciate the attempts of what happened and was discussed in Paris. We have to also appreciate what President Obama has said. There is such a thing as being too late, but when it comes to climate change, that hour is upon us. That's based on scientific information, not just somebody's wise idea. So we really need to be concerned about this. Other paleo data also suggests an acceleration in sea level rise. This is a paper by John Woodruff, again, looking at the vulnerability of the coastlines with rising sea level and particularly with storm surges. So I just want to make, again, final point here that the IPCC estimates that you see here with the various scenarios that were put forward have suggesting sea level 60 to 80 meters above present, depending on which scenario you take. But these did not include the new mechanics of these ice shelves and the unstoppable retreat that scientists are now seeing happening. And so this is really a concern because obviously we have a lot of infrastructure within close to sea level rise, and we have a lot of people in very poor countries that are living in low-lying areas like in Bangladesh. So how are we going to manage these coastlines? How are we going to think about this inevitability that sea level is rising, and it may in fact be accelerating. And we see the acceleration, and we see also what's happening to the ice sheets. The other thing that is important here is that the Lake Ovehicken record, comparing it to the Antarctica record, shows us that, in fact, these ice sheets have come and gone before and unfortunately have not been stable. The Antarctic ice sheet has not been stable for 15 million years, and that it's much more vulnerable. So I want to show you this quote just to give you some perspective, and I think Andy Rifkin pointed this quote out to me some time ago, and I just think it's brilliant. And I'm just going to ask, does anybody know who said this? I'd put my money on the sun and solar energy. What a source of power. I hope we don't have to wait until the oil and the coal run out before we tackle that. And you might be surprised, but this is Thomas Edison speaking to Henry Ford and Firestone in 1931. Okay? So we got to get on to in the right direction with what we're doing with the atmosphere. And I like this quote, this Chinese proverb: we don't change the direction we're headed, we're going to end up where we're going. And with that, thank you very much, and I'll take your questions.
So thank you very much, Julie. Appreciate the presentation. Does anybody in the room here have any questions? I have a question from online here, and this is, believe it or not, from the Innoko River School in Shagaluk, Alaska.
Wow.
And the models that you show, do they have a graphic showing what Antarctica will look like in 100 years or 200 or 500 years?
Yes, I didn't show that simply because the paper is very much in press, but the DeCanto and Pollard have put together an animation that walks you through the Antarctic ice sheet through time. So what I can say is that more than likely Rob will have that available. And if they want to send me an email, I can talk to Rob and get that animation to them.
Fantastic. A few questions from a 9th grade class at Oneida High School in New York. From Stephen, there's a question: if the water levels rise too high, what's our go-to action?
Well, it's obviously really a difficult one, because as sea level rises, we have some management tools in front of us. One thing that's pretty important is that we probably need to get out of, the government needs to get out of the insurance business and not insure people who want to live at the coastline. That as homes are destroyed in various storms that are inevitably going to come up the coast, maybe we need to remove and retreat those communities into areas of higher ground. That's been a very difficult political choice to make. Many of us might argue that the 9th Ward in New Orleans should have been moved to higher ground, not allowed people to move back in there. That's a really difficult choice, because we, as Americans, tend to say, well, we're gonna rebuild and we'll be tough. But at some point, it's going to cost way too much, and you cannot build levees high enough to protect our entire coastline. So we do have to have a management of retreat, and we need to deal with it. My personal opinion.
So here's a question from Ben, and the question is: if we could actually address global warming, will the Arctic gain back the ice in any reasonable time frame?
Yeah, we're pretty much committed to a pretty long period of time in order to pull down CO2 to, for example, let's say have the sea ice come back and grow. Because of the amount of heat that's already been absorbed in the ocean and the atmosphere, so it's going to take a long time for that to be reversed. Even, as I said, we're looking at probably in the range of tens of thousands of years by some estimates, but we can actually slow it down if we can pull. And in fact, this is where geoengineering, Academy report suggesting more information about how can we sequester CO2 and pull it out of the atmosphere with engineering to decrease the carbon dioxide in the atmosphere. We need to change our output, but also then take that out of the atmosphere faster than we might find possible, so that we can accelerate and stop the warming and slow it down. That's our best option.
Any other questions in here? I have a question here from that same class. It says, is it too late to be able to fix this?
No, I'm an optimist. I think we can slow it down, and we just need to be smart about it and very quickly get ourselves off of fossil fuels and we can do this. We have the capacity with wind power and solar and hydro to do that right now. We just need to make a massive change over the next decade or two and try to get that to move forward. And that we can actually slow it down. Can we stop it completely? Probably not. But we can certainly slow it down and change the direction we're headed. So remember, the IPCC has both the best case scenario, and this is having the peak carbon dioxide atmosphere being about right now or the next century, or over the next decade, and then we start to decrease CO2, and that actually makes a big difference in the amount of sea level rise. I think that's the scenario we want to be on. But you know, as you saw in the diagrams, business as usual is not going to put us on a very good trajectory.
Yes, if we still have time. What was the reason of decreasing CO2 in historical cycles?
Yeah, so that's a good question. Why was carbon dioxide at 400 parts per mil 3 million years ago? Well, if we look at the geologic record, if we go back, say, 65 million years ago to the time of the end of the dinosaurs, carbon dioxide in the atmosphere may have been 1,000 to 2,000 parts per mil, are our best estimate. The entire world was tropical. We had dinosaurs on the North Slope of Alaska. The whole world was tropical. And during that time, we had tectonic movements of plates on the continent and the continents and the oceans moving around with the uplift of different mountain ranges and so on. We actually get increased weathering of rocks, of silicate rocks, and the weathering process going from feldspar to clay actually takes in carbon dioxide. So we call it the rock weathering thermostat. Go back and black another term. With the uplift of the Himalayas, with mountain building events, we have increased weathering, and then that brings down CO2. So we went from 1,000 parts per mil down through 500 parts per mil, down to 400 parts per mil. So we were on a trajectory of decreasing CO2 because of that rock weathering thermostat. So what we've done is reverse that trend in only 100 years.
Great. One last question. Says, and this is from Helen, it says, great presentation. In your opinion, what do you think is the most important line of paleo research to help us understand future sea level rise?
Well, I think there are a number of people trying to address this. I think we need to go back and use some of our more modern dating and geochronology techniques to date these shorelines around different parts of the world so that we can understand the magnitude of sea level change on particular coastlines. So the amount of sea level rise that might happen on the east coast of the United States is not going to be the same as the sea level rise in Japan or in Brazil. We need to have a look at that. The new geophysical models are suggesting that if meltwater comes from Antarctica, you have a larger sea level rise in the northern hemisphere. If the meltwater comes from Greenland, you have a larger sea level rise in the southern hemisphere. With these kind of complexities. So I think that learning more about and better dating of these shorelines is really a good start on trying to understand sea level rise into the future.
Terrific. Well, thank you very much. Let's join we are going to be doing these seminar series monthly. The next presentation is going to be on February 18th, featuring Jennifer Francis, and she's going to be talking about the connections between the Arctic and weather. So that should be a very interesting presentation. I encourage you to sign up for that. You can sign up at the address online here. Also, one last note, please complete the evaluation survey either online or face-to-face here and turn it in at the front desk. We really would like to continually improve these seminars, make them as useful to you as possible, and we really appreciate your coming. Thank you very much for taking some time, and thank you, Julie, for a wonderful presentation.
Thank you very much.